Welcome for the third lecture on the series of digital signal processing. In this lecture, we'll be learning linear convolution using circular convolution and linear convolution using DFT IDFT method. The circular convolution is a concept that we have learned in a previous lecture. If you have not seen, you can watch that previous video, lecture 2 on DSP. Before we start, we'll recall what is linear convolution of two finite length sequences. Suppose x of n is a first sequence and x2n is a second sequence, then the linear convolution of x1n and x2n is computed by using this equation: m ranging from minus infinity to plus infinity, x1m and x2 of n minus m, where m is a dummy variable, and the resulting convolution output will have length is equal to length of first input plus length of second input minus 1. So x1 has length n1 and x2 has length n2, then our output in a linear convolution will have length n1 plus n2 minus 1. For an example, I have shown a rectangular pulse here in a discrete domain which has 6 samples, where I have 6 number of samples. If I perform linear convolution of this pulse with this signal itself, then the resulting output will have 6 plus 6 minus 1 number of samples, and that is what you can see in a result of linear convolution of x1n and x2n. With this basic knowledge, we can start with linear convolution using circular convolution. To obtain the linear convolution, we must ensure that the circular convolution has the effect of linear convolution. What do I mean by this? Let us consider an n1 point sequence x of n and another n2 point sequence, which is actually an impulse response of a system, h of n. Now, if I perform linear convolution of x of n with h of n, the resulting output will have capital N1 plus capital N2 minus 1 number of samples. Consequently, for the linear convolution and circular convolution to be identical, we must have the length of circular convolution equal to N1 plus N2 minus 1. Then only the result will also have length N1 plus N2 minus 1. That is, the both sequences x of n and h of n must be augmented with sequence of 0 amplitudes, and that procedure is generally referred to as zero padding. So what we'll be doing, we'll be first performing zero padding and then we'll perform the circular convolution. The result will be same as linear convolution. So here is a procedure. For linear convolution using circular convolution, we first have to pad the zeros at the end of both sequences to make lengths equal to n1 plus n2 minus 1 each. Then we perform the circular convolution of those two sequences, and the circular convolution result will have length n1 plus n2 minus 1. This circular convolution will be same as the linear convolution because there is no overlap in the periodic repetition of the original sequences which we have used, as we have introduced a zero padding in them. Now, to perform linear convolution or that linear filtering using DFT IDFT method, we have to go in a frequency domain instead of using a time domain. Why we use DFT IDFT for performing linear convolution? The reason is efficient algorithms for computation of DFT and IDFT are available. So it will be feasible to perform that linear convolution in a DFT IDFT method instead of using a time domain method. So procedure for that will be somewhat similar. First step is we have to pad zeros at the end of both the sequences to make their lengths n1 plus n2 minus 1. Then we compute the DFTs x of k and y of k of those zero padded sequences. Both DFTs will be of length n1 plus n2 minus 1. Then we find a product of x of k and y of k. Let's call that as a z of k. This will again have length n1 plus n2 minus 1, and this is a DFT of a convolution result. That z of k is actually a DFT of a convolution, linear convolution that we are intended to find. So we compute the IDFT of that z of k, which will have again n1 plus n2 minus 1 number of samples, and that IDFT is nothing but linear convolution result. So the procedure can be shown in a graphical way like this. We have a n1 length sequence x1n. We have another n2 length sequence x2n. If we perform direct linear convolution, the result will have n1 plus n2 minus 1 number of samples. Instead of doing this in a time domain method, we can do this in another method called as a DFT IDFT method, where in a frequency domain we actually perform the circular convolution of two sequences. So we initially make their lengths equal to n1 plus n2 minus 1 by zero padding. Then we compute DFTs, we multiply those DFTs, and we compute that IDFT of size n1 plus n2 minus 1, which will result in a linear convolution result. Thank you.